Okay, folks, so I want to graph one more of these, and we're looking at the graph of this function right here. There'll be some curious points to this. So, running through our steps, the first thing we want to identify is the domain. And what's the domain of this function? It goes from minus infinity to 0, union with 0 to infinity. The x squared factor is defined for all real numbers. The natural log expression is only defined for positive values. Well, x squared is certainly positive for everything except for x equals 0. So this is defined for all real numbers except for when x equals 0. The next thing we want to identify are the zeros of this function. So how do we find the zeros of a function? Well, we set the function equal to 0. That happens when x squared times the natural log of x squared equals 0. That happens when either of its two factors are 0. So that happens when x squared equals 0 or when the natural log of x squared equals 0 by the zero product property. Okay, well this happens when x equals 0, but what? Before we call that a 0 of the function, we initially said the domain was everything except for 0. So even though that's a true statement, that if we plug in 0 for x, well, it's actually not even a true statement because it wasn't the domain of the original equation, so we have to throw it out. Okay, but looking at the second factor, when is the natural log of x squared equal to 0? Well, it's the same time when e to the 0 is equal to x squared. So what did I do there? There's two ways of thinking about that. One is that I raised both sides to the power of e, but the better way to think about it, I think, is I wrote the logarithmic statement as its equivalent exponential statement. Well, what is e to the 0? It's 1. And so if we solve for x, we get plus or minus square root of 1, or we get x equals plus or minus 1. So the zeros are the x-intercepts then are at negative 1 comma 0 and at 1 comma 0. Those are the zeros of this function. Okay. Now let's go looking for a y-intercept if we can. Well, how do you find a y-intercept? Well, normally what you would do is you take your function, and if you're looking for the y-intercept, you're going to input a 0 value for x. But this is undefined in this case. Again, we identified the domain to begin with, and we said we could not plug in the number 0. Okay, so now we want to look for vertical asymptotes / holes. How do we find vertical asymptotes and holes? Well, we go through and we explore the boundaries of the domain. Well, this function was undefined at x equals 0, so we should explore the limit there. Let's look at the limit as x approaches 0 of x squared natural log of x squared. Now, normally when I'm looking at a limit approaching an exclusion in the domain, I might need to pick a direction of approach. But notice that both these quantities here, for the first factor and for the argument of the second factor, are being squared. So the direction of approach doesn't matter in this case. So we can just say as x approaches 0. Okay, well, let's identify this structure of this problem. The first factor is tending towards 0, but the second factor is tending towards negative infinity. So this is an indeterminate product, and we can't determine what that will be ahead of time. So we need to apply, well, we would like to apply L'Hopital's rule, but we can't apply it just yet. Why not? Well, because L'Hopital's rule doesn't work for indeterminate products. It only works for the two specific indeterminate quotients that we mentioned. So what could I do? Well, the best choice is to take this first factor down below the line and invert it. Okay. I could have brought the natural log of x squared below the line and inverted it, but when I applied L'Hopital's rule, I would just end up with a mess. So in looking at these two, again, when you have an indeterminate product like this, you take one of the factors below the line and invert it. And the best choice is to take the x squared factor below the line. Okay, so this gives us the limit as x approaches 0. Now we're ready to apply L'Hopital's rule. How come? Because now this has indeterminate form minus infinity over infinity. So L'Hopital's rule now applies. We're applying it. Taking the derivative of the numerator, we get 1 over x squared times 2x, all divided by minus 2 over x cubed. Okay, so I took the derivative of the natural log of an expression, that's 1 over that expression, times the derivative of that expression. and the derivative of 1 over x cubed, we think of that as x to the minus 2 power. Then when we take its derivative, that's what we end up with. Okay, so we're getting closer to being able to evaluate this. Let's go ahead and clean it up a little bit. We get the limit as x approaches 0 of the numerator just cleans up to be 2 over x, all divided by minus 2 over x cubed. Inverting and multiplying then gives us x cubed, that should be x there. Inverting and multiplying the denominator to multiply these two fractions together gives us this expression, which is the limit as x approaches 0 of negative x squared, which is just equal to minus 0 squared, which is equal to 0. So what did we just determine? Way back up here, we were looking for our vertical asymptotes and holes. To determine where those are, we're going to explore the exclusions in the domain with limits. We took the limit of the exclusion in the domain and found out we got a value. And so what have we just shown? We have just shown that this graph has a hole at when x approaches 0, and the y-coordinate is also 0 there. So this is a hole at 0, 0. Okay, let's keep going. Now let's go ahead and find, I'll just keep going down. It's a little bit easier. Now let's go ahead and find our horizontal asymptotes. So to find the horizontal asymptote slash the end behavior of this function, we're going to look at the limit as x approaches both plus and minus infinity of this function of x squared, natural log of x squared. Normally I have to treat those two separate, but again, because both factors are being squared in terms of the x, both times x shows up, it's immediately being squared, the direction of approach doesn't matter. So approaching infinity or minus infinity is the same thing. That's kind of philosophical. All right, so notice that in either case, when I take either plus or minus infinity and plug it into the first factor, it gets squared, so it's an arbitrarily large positive number. And when I plug in plus or minus infinity to the second factor for x, it gets squared, so it's arbitrarily large positive. Then I take the natural log of an arbitrarily large positive, which is still arbitrarily large and positive. So this has the form, let's just say that this, not the indeterminate form. Notice I'm not writing IF, I'm just putting the form infinity times infinity, and there's no ambiguity there. That is infinity. Okay, so we found the horizontal asymptote slash end behavior. So at long last, we're starting to look at the derivatives because we want to identify where we're increasing, decreasing, spot any local maxes and mins. And we also want to identify where we're concave up, concave down, and spot any inflection points. So let's see here. Let's take f prime of x. So let's see, I'm going to recopy f of x just so I've got it ahead of me. Natural log of x squared. So we're going to have to do a product rule. We'll call this the first factor, this the second factor. So when we do the product rule, we get the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. Let's clean up this mess. We end up with 2x plus 2x natural log of x squared. Factoring out of 2x gives us 2x times 1 plus the natural log of x squared. I want to identify the critical numbers of f. Remember, the critical numbers of f are where the derivative of f is either undefined or 0 for interior points in the domain. Well, the first derivative of f is undefined when x is 0, but that x value is already excluded from the domain, so we're not going to pick that up as a critical number. Don't worry, we'll explore the behavior there anyway. But then we could ask the question, when else could this be 0? Well, it would happen if 1 plus the natural log of x squared equals 0. So when does 1 plus the natural log of x squared equal 0? That happens when the natural log of x squared equals -1. Well, when would that happen? Well, let's see. I can't solve that in my head. Let's rewrite it as its equivalent exponential statement. So that happens when e to the -1 equals x squared. That is when x squared equals 1 over e. So that would happen when x equals plus or minus the square root of 1 over e. Or we could write plus or minus the square root of 1 over the square root of e. Either of these is acceptable. Okay. So those are our critical numbers of f. Now let's go ahead and look at the second derivative here. Spots out of there. So the second derivative, let's see here. I'm going to recopy the first derivative. We said it was 2x plus 2x ln of x squared. So now let's go ahead and find the second derivative. So the second derivative is differentiating termwise. There's the derivative of the first term. And then I'm again going to have to do this product rule. So let's see here. This would be the first times the derivative of the second, whoops-a-daisy, times the derivative of the second, 1 over x squared times 2x, plus the second, natural log of x squared, times the derivative of the first. When we clean everything up, let's see here, we have this 2 plus, let's see here, that gives us 4x squared over x squared, so that's just plus 4, plus 2 natural log of x squared. So this simplifies to be 6 plus 2 ln of x squared. So where is this, so let's find the critical numbers now of f prime. Remember, the critical numbers of f prime will be where its derivative, the second derivative, is either undefined or where it has zeros. Well, its derivative is undefined at 0, but so is the derivative of f, so that's not going to be a critical number. But we could have the instance where 6 plus 2 times the natural log of x squared is equal to 0. That would happen when 2 times the natural log of x squared is equal to negative 6, or when the natural log of x squared is equal to negative 3. I can't solve that in my head, so let's go ahead and rewrite it as its equivalent exponential statement. So what's its exponential statement? We would say that e to the minus 3 is equal to x squared, or plus or minus the square root of 1 over e cubed is equal to x squared, equal to x, applying the square root method. Or what could we do? We could also say that x equals 1 over e to the 3/2, plus or minus. So might have been a little bit fast. Let's see here. The square root of 1 over e cubed is the same thing as the square root of 1 over the square root of e cubed. But that's the same thing as just 1 over e to the third to the 1/2 power. Square rooting and fractional power 1/2 are equivalent, and we get 1 over e to the 3/2. So that's what I got that from. Okay. So we've got our critical numbers, and if you go way, way back up to my problem statement, way up here, you'll see that I went ahead and gave you decimal approximations of those critical numbers, because I don't know what those are off the top of my head, and that gives me a sense of where they'll fall on the number line. So I'm ready to now create my number line. So here we go. I'm going to put a number line up here, and what am I going to do? Well, I'm going to first put all the places where the original function is undefined, any exclusions in the domain of the original function. So I've got to put 0 up there. Then I'm going to put all the critical numbers of f. Well, f had critical numbers at 1 over the square root of e, I believe. Is that what we had? That should be a minus sign, but yeah. Minus 1 over the square root of e and 1 over the square root of e. So these were when f prime of x were equal to 0. When f prime of x was equal to 0, whereas this is where f is undefined. Then we also should put up where f prime has critical numbers, the potential locations for our inflection points, and those happen at 1 over e to the 2/3 minus, and at 1 over e to the 2/3. So we've got our number line, and this is kind of a messy one. That's why it was helpful to have decimal approximations up there. Remember, this is about -0.6. This is about -0.2, was that what I said? I forget. -0.22. This was about 0.22, and this was about 0.6, or thereabouts. Okay, so I can now take test points on all sides of those. So let's go ahead and do that. Okay, so we could take, for instance, -1, -0.5, -0.1, 0.1, 0.5, and 1 as our test points. And then we can determine, well, we'll first determine the intervals for which we're increasing and decreasing. Okay. Now folks, I'm going to cheat a little bit here. To be honest, evaluating these would take some time. If you plug -1, if we were to plug -1 into our first derivative, sorry, I'm probably giving you motion sickness here. Where is our first derivative? Here it is. If we were to plug -1 into our first derivative here, and then decide the sign, well, it would take us a little bit to figure this out, but it turns out that we would be decreasing. Okay, so I'll let you check that. And if we were to plug in -0.5, we would be increasing, and again increasing, and then decreasing, decreasing, increasing. So you can check me on those. We've done this half dozen times now. We've plugged these test points into the first derivative, and we've looked at the sign. Okay, again, doing that takes a little bit of time. I went ahead and computed those beforehand. So then we could look at f double prime of our test point. What are we deciding on these intervals? We're deciding the concavity. So let's see here. We go up to our second derivative. Usually you want to do this in factored form, although you don't have to. I guess I never factored the second derivative. But if we plug -1 into the second derivative, we can determine the concavity. But that would take a little bit of checking. But if we do so, that would take a little bit of checking, but if we did so, we would find that we are concave up, and then concave down, because the sign there changes from positive to negative in that interval. And we would still be concave down, concave up, concave up. Okay. There is a little bit of a pattern here you might recognize. Our original function, I didn't say this, our original function was an even function. And so that means that its derivative will be an odd function, and the second derivative can be even, which is why you have the two patterns that you see in the intervals for increasing, decreasing, and concave up, concave down. Okay, so I think we're ready to graph this thing. All right, we'll go ahead and do this. Ooh, that's not going to give me enough room. All right, let's go ahead and graph this thing. So, and again, on an exam, I would give you a prefabricated axis, so you don't have to worry about scaling and whatnot. But let's see what we can do here. So, let's start putting in the interesting points. Well, we said that at -1 and again at 1, we had zeros to this function. So our function was 0 there. 0 there. We said we had no y-intercepts. Okay, there are no y-intercepts. And then we said we had no vertical asymptotes, but we did have a hole where? We said the location of our hole was at 0, 0. So we got a hole there. Then we said that our long-term behavior, as we went far to the right, we go up, and as we went far to the left, we go up. You look at the long-term behavior statements. So our graph is looking sort of like this. Okay. Then we had 1 over the square root of e, which is about -0.66. So maybe I'll put it there, -1 over the square root of e. And we also had +1 over the square root of e. And if we evaluate those in the function, here I'm going to have to go up and see what we'd said. When we plug 1 over the square root of e into the function, we get about -0.37. Okay. So I'll put those way down here. We get, oops, blue. We get this point right here, and this point right here. That's 1 over the square root of e, comma, and then I'll just put approximately -0.37, and 1 over the square root of e, minus 1 over the square root of e, comma, approximately -0.37. And folks, in the statement of the problem, I only told you this fact, but because this is an even function, then that fact must also be true. Okay. Then we need to put up our two inflection points that we found. We found that we had one at 1 over e to the 3/2, and another one at -1 over e to the 3/2. And we could place that inflection point here and that inflection point here. And let's see here. What did we say the approximate values of those were? We said that f of the location of that is approximately -0.15. So this is about negative 0.15. Let's see, probably label this here. So this would be 1 over e to the 3/2, comma, approximately negative 0.15, and 1 over e to the 3/2, oops, that's minus, comma, negative 0.15. Ooh, it's got ugly. Okay, so we're ready to, now we've got our points plotted, we're ready to put this all together using our increasing, decreasing / concavity chart. So before we get to this point of this, notice this is a local minimum here. Before we get to the point of that local minimum, we're going to be decreasing in a concave up manner. So before we get to right here, we're going to be decreasing in a concave up manner. So let's see here. Here we are decreasing in a concave up way. Go ahead and erase that arrow now. Then, according to our chart, we've got a local minimum there because that was a critical number, right? That was a critical number, so that gave us a local minimum. Now we're going to be increasing in a concave up manner. So we sketched the curve. Now we're increasing in a concave up manner until we get to this inflection point. At the inflection point, let's see here. Here's the inflection point. We know it's an inflection point because that's where we changed from concave up to concave down, and it was a point defined on the original function. So we got an inflection point because we continue increasing, but now we do so in a concave down manner. So we continue increasing, but in a concave down manner. All right, that looks pretty ugly. I'm going to go ahead and fix that real quick. I might erase a little bit, but that's okay. So let's get that cleaned up just a little bit, increasing, great. And then we arrive at this hole. So notice I'm not putting a point in that hole. Make sure it doesn't look like there's a point there. I'm blotching this up, but we'll survive. Okay, and then after I leave the hole, okay, and this is why I wanted to put 0 on here. Even though it's not a local max or local min or inflection point, anything like that, stuff still happens at that undefined point of the graph. So I did need to include that in my chart. And we notice that we begin, oops, where'd it go? Okay, after we leave the hole, we will be decreasing in a concave down manner. So we're decreasing, but in a concave down manner until we get to this point of inflection, at which point we change our concavity. We will continue decreasing, but now in a concave up manner. We arrive at our local minimum right here, and we continue increasing in a concave up manner after we leave the minimum. And there we have the graph of this function with all of the interesting points labeled on it. That's good enough for sour apples.